All right, so this lesson is all about simplifying radicals and doing radical operations. So a radical is an expression in the form here, where n is called the index and b is called the radicand. All right, so what we're going to do is we're going to simplify some radicals, and there's kind of multiple ways to do this. I'm going to show you the longer way, and then I'll show you the shortcut. So when we're looking at number 1, we have 48 under the square root. So we're only ever concerned about simplifying what's under the square root. Anything outside of it, we're just going to leave that until the end. So I'm going to go over here and I'm going to write 48, and I'm going to start breaking down 48 and thinking about what can I divide 48 by. So there's a bunch of different options. We can do 12 and 4. Then we need to break those numbers down. So I can break down 12 to 3 and 4, and then I can break down 4 to 2 and 2, and break this 4 down to 2 and 2 also. So what we're looking for is groups of 3. So anything that is anything that has a pair, so we have 2 2's, we have 2 more 2's, those are all going to go to the outside of our function. So we already have a 5 out there. That's just part of our equation. And then now we have these 2 2's that we're going to pull out. Okay, but then we have a 3 left over. That's going to stay underneath the square root. So we have a 3. So then we can kind of do the same thought process with our x's and y's. So if you write out all of your x's, we have 2 x's. I'm just going to write it above. We have 2 x's and we have 5 y's. So all of those are being multiplied together, and we're looking for groups of 2 because it's a square root. We have 2 x's, which means we'll have 1 x on the outside, and then we have 2 groups of y's, so we're going to have y squared on the outside. And then on the inside, we're going to have just this y left over. All right, and then once we do that, then we're going to go ahead and just multiply outside, or multiply whatever we can. So 5 times 2 times 2 would give us 20 xy squared square root 3y. All right, and that would be our simplest answer. So if we look at the next one, now we're looking for groups of 3 because of that cube root. So because the index is 3, we want to have 3 in each group. So we're going to break down 108 first. So 108, there's multiple things we can divide it by, so there's no right first step, but I'm going to divide it by 27 and get 4. Break down 4 and we have 2 2's. 27 is 9 and 3, and then 9 is 3 and 3. So we're looking for groups of 3, so we have 3 3's, and we only have 2 2's, so we can't do anything with those 2's. So we're going to have 1 3 on the outside, and then we're going to have our 2 2's left on the inside, so 2 times 2. All right, and then we can do the same thing we did on the other problem with our y's and z's. So we have 1 2 3 4 5 y's, and we have 1 2 3 4 z's. So I'm going to circle groups of 3. So we have 3 y's. So we're going to have 1 group of y on the outside, and then we have 2 y's left on the inside. And then we have 1 group of z's, so I'm going to have 1 z on the outside, and then 1 z left on the inside. All right, and then we need to multiply everything that we can. So we have 3yz on the outside, cube root, 2 times 2 is 4. We have 2 y's, so we're going to write that as y squared, and then we have z. All right, I want you to try number 3 on your own, and you can check your answer on Schoology. All right, so let's look, or be careful with number 4 because you have, sorry, number 3, your index is 4, so you're looking for groups of 4, okay? All right, so multiplying radicals. So we can multiply radicals together as long as the index is the same. So remember, the index is the number of our root. So if we look at number 4, both of these are square roots, so we can multiply them. And the easiest thing to do is just to multiply the two numbers that are underneath there. So negative 24 times negative 18 is going to give us 432. And then we're going to break it down. So here's where I'm going to show you your shortcut. So absolutely do the tree if you don't like the shortcut or if you don't understand the shortcut. But the best, or like the quickest way to solve these kind of problems to simplify is to figure out what is the biggest square root that we can divide 432 by. So what is the biggest perfect square? So you can try a couple things, like you could try 16, and that'll leave us with 27. So I'm going to try to go a little bit bigger, and I'm going to try like 81. 432 divided by 81 is a decimal, so that's not going to work. But if we do 432 divided by 144, then that leaves us with 3. So if we were to break this up to be 144 and 3, we know that the square root of 144 is 12. That's our perfect square. And the square root of 3, we can't do anything with. We can't simplify it at all. So then that would be our final answer. So you can still go through over here and do 432 and draw your tree and divide it all the way down. It'll take you a little bit more time, but it's definitely still an appropriate approach. All right, so for the next one, I'm going to multiply for you, and I want you to finish it by simplifying. So we have both cube roots now, so we're just going to multiply what's underneath. So we have a cube root, and we're going to do 18 times 9. 18 times 9 is 162. And then we have 1y here and 4 y's here, so we have y to the 5th. All right, so now I want you to simplify on your own and check your answer on Schoology. And remember, you're looking for groups of 3 because it's a cube root. All right, adding and subtracting radicals. So we can only add or subtract radicals if they have the same index and have the same radicand. So they have to be like terms in like every aspect of the word. So I'm going to use my shortcut to simplify all of these because our first step should always be to simplify our radicals. So 50, we can divide that by 25, which is a perfect square. 50 divided by 25 is 2. So the square root of 25 is 5. So we're just going to have a 5 on the outside now, and then that square root of 2 is going to stay. We can divide 500 by 100, which we know is a perfect square, and 500 divided by 100 is 5. So we're now going to have a 10 on the outside and a 5 left on the inside. All right, and then for the next one, 125, we can also divide that one by 25, and we're going to be left with 5. So 125 divided by 25 is 5. So we're going to have minus 6. The square root of 25 is 5. And then we have square root of 5. All right, so then we're going to multiply the outsides. So 2 times 5 is 10, plus 40 square root 5 minus 30 square root 5. So we can only add or subtract if what's under the radical is the same. So this 10 square root 2, none of the other radicals have a 2 underneath it, so we're just going to write 10 square root 2. We can't combine that with anything else. But because both of the other radicals have a 5 underneath it, then we can subtract those. So 40 minus 30 is going to give us 10 square root 5. And that would be our final answer. So as long as you know how to simplify and you know how to add them together, you should be good. All right, so looking at number 7, I'm going to walk through this one with you. So number 7, if we're looking for perfect cubes, so remember, think about your perfect cubes as like 1, 8, 27, 64. We probably only really need to know those. So let's think about what can we divide 54 by? That's one of those perfect squares. So we can divide 54 by 8. Sorry, not 8. We can divide 54 by 27, and that would leave us with 2. So we can split this up to be cube root 27, cube root 2. So that means that we would have a 3 on the outside because the cube root of 27 is 3, and we'd have a 2 left on the inside. And then we need to worry about our variables. So you can do the thing where you write them all out, or you can figure out how many times can you fit 3 into 4. So we can fit 3 into 4 once, and then we have 1 left over. And then same thing for y's. We can fit 3 into 6 2 times, and we would have none left over. So we'd have none left under the radical. All right, so for the next one, the perfect square we can divide 24 by would be 8. And 24 divided by 8 is 3. The cube root of 8 is 2. And then we're going to do our variables. So how many times does 3 go into 3? 1 time, so we're going to have 1x on the outside. How many times does 3 go into 9? 3 times, oops. So we're going to have 3 y's on the outside. So we're going to have y cubed. And we would have none left on the inside since 3 fits evenly into both of those numbers. So on the inside, all we're going to have is this cube root of 3. All right, and then for the last problem, so cube root, let's see what we can split up 128 to. We can divide 128 by 64 and be left with 2. So we're going to have plus, this cube root of 64 is 4, cube root, and we're going to have just that 2 left on the inside. And then we want to see how many times does 3 fit into 4. It's going to fit once, and it's going to have a remainder of 1x. And then 3 fits into 6 2 times, and we'd have none left on the inside. So that's a lot of work just to simplify because we haven't even added or subtracted yet. But what we're looking for is like terms. So they have to have the same radicand. So that means the same exact thing underneath the radical, which these two do. It also has to have the exact same variables on the outside of the function. So we have xy squared, xy squared. So we can go ahead and add those numbers. 3 plus 4 is 7, and then nothing else changes. So we just leave everything else the same. And then the last thing we have is just this term that didn't have any like terms. We just leave it the same. All right, and that would be your final answer for that one. I'd say adding and subtracting is like the more involved part of this unit, but it's not too bad. All right, so changing between exponential and radical form. So this is where we have, if we're given a fraction as an exponent, then we need to know that that means that we have a radical of some sort. So it's always exponent over index. Index is the number outside of the radical. So if we look at number 8, we're going to write these as radicals. So we have 4 as the bottom of both of them. So that means that we're going to have a 4th root. And then we just have 2 to the first power, which is just 2. And then we have a to the 3rd power. All right, looking at the next one, we just have a number now. So we're going to go ahead and write this. We have the square root of 300 cubed. So we have a square root because the denominator is 2. square root means we have an index of 2. And we have 303 times. So we could type it into the calculator, but it's going to be a very big number. So what we're going to do is we're just going to go ahead and write 300 3 times. And just like we did above, we want to simplify. So we're looking for groups of 2. So we have 2 300s. So we can pull 1 300 out, and we have 1 300 left on the inside. Then we can simplify 300, and then that's a little easier of a problem to look at. So 300, we can break it up to be 103. So we would have 300 times 10 square root 3. So that would be 3,000 square root 3 for that one, which is a very big number. All right, and then the last one, we're going to get a common denominator so we can write these all under the same radical. So if we look at this, we can multiply, or the biggest denominator is going to be 8. We want them all to have that denominator now. So if we want a fraction that has 2 as the denominator to have a denominator of 8, we're going to multiply the top and bottom by 4. And if we want a fraction that has a 4 as the denominator to have an 8, we're going to multiply the top and bottom by 2. So we can rewrite this as a to the 4 over 8, b to the 3 over 8, c to the 2 over 8. So all we did was just get a common denominator, and now we're going to write it under a root. So we're going to have the 8th root, because all of them have a denominator of 8. That's our index. We have a to the 4th, b cubed, and c squared. That's all based on the numerator. All right, and then we're going to go the opposite direction too. So if we have the cube root of 27, you need to know that that's a perfect cube. The cube root of 27 is 3. And then we're just going to write the rest of it as fractions. So a to the 5 over 3, the exponent is 5, the index is 3, and b to the 2 over 3. All right, then looking at the next one, we have x to the 3 over 4, y to the 8 over 4, and we want to see if we can simplify those fractions, we should do it. So we can't simplify 3 over 4, but we can simplify 8 over 4, which would just be y squared. All right, so next we're going to talk about exponent rule review. So x to the a times x to the b, our rule is x to the a plus b. So we add exponents when we're multiplying bases. If we look at the next one, when we're dividing, we would subtract the exponents. So a minus b. So we're going to go ahead and solve these. So if we're multiplying two common bases to each other, all we do is take the exponents and we're going to add those together. So don't forget, when you add fractions, you have to get a common denominator. So we're going to make our common denominator 6, because that's the smallest number that we can make 3 and 2 fit into. We're not going to multiply that by 3 over 3. We're going to do it by 2 over 2. So then we would have 3 over 6 plus 2 over 6, which is going to equal 5 over 6. So that's a lot of work just to say that this given problem is equal to x to the 5 over 6. All right, next one, now we're going to subtract our exponents. So because it's division, we want to do 4/3 minus 1/3. They already have a common denominator, so all you have to do is get 3 over 3, because 4 minus 1 is 3, which is just equal to 1. So this whole ugly fraction is just equal to 7 to the first power, which is just 7. All right, and then last thing, we're just going to multiply. So when we have a number outside of parentheses like this, we just multiply. And remember, this is the same thing as 6 over 1. So we're going to have n to the 12 over 3. So we just multiply the numerators and multiply the denominators. And then simplify, because 12 divided by 3 is 4. All right, and then next part is solving radical equations. So don't forget that if you have an even function, then you need to find the restricted domain. So what we're going to do is set what's under the radical greater than or equal to 0, and that tells us our restricted domain. So x is greater than or equal to 1. I also want you to notice that there's an x on the outside of the equation, which means we need to check our solution. So we have a little more work whenever that happens, because we might get a solution that works in our restricted domain, but isn't going to work when we plug it in. And that's because if we get a negative on the outside, then it's going to throw everything off. So what we're going to do is subtract x from both sides first to get our square root by itself. And then we're going to square both sides. And don't forget that for this, we need to FOIL. So we need to do negative x plus 3 times negative x plus 3. So on the left side, we have x minus 1 equals, and then we have x squared minus 3x, minus 6x plus 9. And then because we have an x squared, we're going to get everything to one side. So I'm just going to subtract everything from the left side and move it to the right side. So those cancel, and we get x squared minus 7x plus 10 equals 0. And then we factor. So figure out what multiplies to 10 and adds to negative 7. That would be x minus 5, x minus 2. And then so x would equal 5 and x would equal 2. All right, so if we check both of those against our restricted domain, they're both going to work. However, if we were to plug 5 into the original function, 5 minus 1, I'll just do the little math right here. 5 minus 1 is 4, plus 5 equals 3. The square root of 4 is 2, plus 5 equals 3. But 2 plus 5 is equal to 7, and 7 is not equal to 3. So x equals 5 does not work for this function. If we plug 2 in, it does work. So you can go through and check that, but it will work. All right, I want you to solve the next one on your own. Because it's a cube root, you do not need to isolate, but make sure to check your answer on Schoology. I'm sorry, you do need to isolate. You do not need to find a restricted domain. All right, and then imaginary numbers. So when we take the square root of a negative, we get an imaginary number. So the square root of negative 16, we would break that up to be the square root of 16 and the square root of negative 1. The square root of 16 is 4, and the square root of negative 1 is I. And then if we're looking for like a higher power of I, to reduce the power, we divide the exponent by 4 and look at the pattern. So this is where the I1 negative sandwich comes in. So the negatives go in the middle. And if we're trying to reduce a higher power, then what we want to do is look for the decimals. So I is always going to be a 0.25. I squared will be a 0.5. I cubed will be a 0.75. And I to the 4th will be a 0.0. So it'll be like a whole number. So if we do 13 divided by 4, 13 divided by 4 is going to give us a 0.25. So that means that we have an I. And if we look at number 14, 48 divided by 4 is going to give us a whole number, so a 0.0 decimal. So that means that we would just have 1. Okay, so go ahead and make sure you do those problems and check them on Schoology, and then